Everyone, look who's back. It's Professor Thomas. Yes, I know that you missed my videos the past week. Or maybe you've just been watching the ones I've been posting over and over again. One of those two. Anyhow, we're on to the renal system. And the renal system is one of my favorite systems in the entire body because it is so amazing. And I know you're like, all right, Professor, I'm sold. But think about it. You have these two organs in your body that are about the size of a closed fist. Currently, these organs have 25% of your total blood. Yes, 25% of all the blood in your body is currently in your kidneys. On top of that, they are so powerful that even under maximum load, you really only ever need about maybe a third of one of your kidneys, which is why somebody can donate a kidney to someone and be perfectly fine. So, on top of that, some more facts about the renal system is that what it does is that it filters your blood plasma. Your blood plasma is the liquidy part of your blood. Doesn't contain the cells. So any cell does not go into or is not filtered by the kidneys. If it is, you're in trouble. But all the liquid parts of your blood are eventually filtered through the kidneys. And about 180 liters of filtrate a day goes through your kidneys. And when I say goes through your kidneys, I mean is literally separated from your blood and filtered through tubules in the kidneys called nephrons. And despite that massive amount of water that filters through your kidneys every day, only about 1 to 1.5 liters of urine is excreted, which just shows you how efficient the kidneys are at filtering, returning the filtrate to your blood, and being able to eliminate waste from your body without losing too much water. If you think about 180 liters, now this can of energy drink, one of my students told me to buy. It's called Ghost Warhead Sour Watermelon melon flavor. It's all right. Kind of. I just don't like those energy drinks that just have that kind of. It's like they're trying to hide the fact that it tastes bad, and that's exactly what they're doing, but not too successfully. It just is very strong. But anyways, this is a 16-ounce can, about 473 milliliters. So it would be approximately, if my math is right, and I don't trust my math, but it would be over 360 of the volume of these cans flowing through your kidneys in one day. That's how much filtrate is travels through your kidneys in one day. All right, so let's go ahead and talk a bit about the renal system. Okay. So the renal system has a couple of very important tasks, but we're not going to talk about them all. We're just going to talk about the basics. And the first one is that it must maintain what is called your blood volume and blood pressure. Not to get too geeky on you guys, this is stuff we talk about pretty extensively in physiology. But blood pressure, a function of it is how much water is in your blood. And it is a mechanism called the Frank-Starling reflex. But basically, the more filtrate is in your blood, well, not filtrate, the more water is in your blood, the greater your blood volume, then the higher your blood pressure. And of course, you don't want your blood pressure too high long term because it can cause, over time, damage to your arterial walls. So what it does is it makes sure that only the correct amount of liquid is in your blood. So it makes sure that your blood volume is the is the necessary amount, not too much, not too little. And that ensures that your blood pressure stays normal. Because if your blood volume is too high, you have too high blood pressure. And if your blood pressure is too low, then you have too low blood pressure. Well, obviously, but in either direction is not desired. It also removes waste. There's lots of things that your body makes as byproducts that is not needed. So things like, for example, creatinine, which is a byproduct of energy metabolism. Also urea, which is a byproduct of protein metabolism. Xenobiotics are anything foreign that you put into your body. So, for example, medicine. So certain medicines are filtered out of your blood and then excreted from the body. And also excess hormones. So if your body's going to make something that's in too large of amounts, then it's going to be excreted from the kidneys. It also produces hormones. It's actually quite a few hormones that the renal system produces. One is called renin, and the effects of renin are pretty complex. But basically, what renin does is it plays a role in regulating blood volume. So this is one of the main hormones that's responsible for maintaining blood volume and pressure. Aldosterone is secreted from the adrenals, which is found on top of the kidney. So I'll just go ahead and include them for fun. So aldosterone, what this does is it stimulates the functional parts of the kidney called the nephron. It stimulates them to increase sodium reabsorption. Now, why is that? Because there's a saying in nursing school that water follows sodium. And if you take more sodium from the functional parts of the kidney, the nephron, and move it into your blood, then water is going to follow it. So what this does is it's going to increase your blood volume. And also another one is called erythropoietin. Erythropoietin. And what this does is it stimulates red blood cell production. For those of you that are my age, you might remember an athlete named Lance Armstrong, and he became famous because he was a cancer survivor who won the Tour de France multiple times, which I do want to say in his defense, the Tour de France is an absolutely brutal event. I mean, absolutely taxing. I don't think there is one person at a high level that has not partaken in using banned substances. But Lance Armstrong was known to use erythropoietin because the higher your red blood cell count, the more hemoglobin you have, and the more hemoglobin you have, the more oxygen you can carry and give to your cells. So that's a form of blood doping, and you can take extra amounts of erythropoietin and give yourself an advantage that way. All right, let's go ahead and let's draw the kidney. Brown's good kidney color. So this is our kidney. And the kidney has different layers to it. So the first one we're going to draw is called the kidney capsule, and it's a hard outer covering that protects the kidney from damage. Because you see, the left kidney actually sits slightly higher than the right kidney. Because of that, the left kidney is protected by the thoracic cage, and the right kidney is not. Which is why the kidneys also have a fair bit of fat covering them, because it can protect it from physical trauma. The thing is the kidney really doesn't want to be messed with at all, and the fact that there's so many nociceptors on it proves that it will really let you know if you're hurting it. The kidney capsule contains some of the highest density of nociceptors out of any other body part, which is why when someone gets a kidney stone, why it's so excruciating, because there's just so many nociceptors, so many pain receptors that are found in the kidney capsule. Now, the next layer is called the cortex. Cortex means outer. And the cortex actually contains much of the blood supply that is found in the kidneys. And you're probably saying, well, what is the purpose of the blood? Well, what's going to happen is if you recall, is that the job of the kidney is to filter blood, and what happens is that there is a large artery called the renal artery that's going to subdivide into several of these tiny arterioles that is going to enter the functional part of the kidney called the nephron. But anyways, this outer layer is called the cortex. Cortex means out, means outer. And the middle is called the medulla. And the medulla has a very hypertonic environment. You won't be tested on exactly what that means, but just know that it has a very hypertonic environment. That helps with reabsorption. I don't know if I've said it yet, but reabsorption is when filtrate is moved from the kidney nephrons, the functional part of the kidney, into the or back into the blood. Now, in the medulla, there's going to be a number of structures called renal pyramids. And these structures, there's different amounts for every person. How many you have is based on genetics, but usually there's between 4 and 8. I'm not going to draw more than 5, but what these do is that these contain what is called the nephrons. As I said, the functional units of the kidney. And depending on how many renal pyramids you have, there's between I would say maybe 600,000 and a million nephrons per kidney. So the renal pyramid is in the medulla and contains the nephrons. Now, also there are sort of indentations between the pyramids called calyces. Now, what's going to happen is that eventually anything that's going to become urine is going to travel through this part of the renal pyramid called the papillae, and it's going to drain into this larger indentation called the renal pelvis. And the renal pelvis is where what's going to become urine goes. And then the urine is going to go down this long tube here called the ureter. And the ureter is going to drain into the bladder. And then what's going to come out of the bladder is going to be called the urine. So we're going to draw here a nephron. So as I said, is that the nephron is the functional part of the kidney. I'm sure you're getting rather tired of hearing that. Understandable. I'm just going to draw one though, because there's no point to draw more than one, even though there's thousands and thousands in each renal pyramid. Now up here is going to be the cortex. So this is the blood. And this is more than what you need to know, but of course my goal is to educate you guys as much as possible. And what happens is that the blood is going to actually, let me draw it more in the center. The blood vessels called the arterial. What happens is that it is going to turn into a ball of capillaries called a glomerulus. You don't need to know that, so I'm not going to just to spell it out or anything. But this glomerulus is going to be contained in a capsule. So we're going to draw the nephron here. A capsule called the Bowman's capsule. It's going to look like this. No, I didn't do the greatest job of it, but what's going to happen is that blood is going to go through the glomerulus, and some of it's going to be squeezed into the nephron. Not all of it, but some of it, like 20%. And I know you're probably saying, that's it? Well, if you try and take out too much filtrate, then blood flow is going to slow down too much or stop. You don't want that. But considering how often the filtrate passes through the kidneys, how often the blood goes through the kidneys, it's reasonable that it's all going to get filtered eventually. So it doesn't like there's going to be some that just that just is missed. It's going to go through the kidneys so often that it's all going to get filtered. Now, this is not exactly how a nephron looks. A nephron is actually highly twisted, but this is a good way to teach it. So after the Bowman's capsule, it's going to turn into a section, and this section is called the proximal tubule. And the proximal tubule is going to turn into another long tube that really goes down into the renal medulla, and is called the loop of Henle. And I know I'm not labeling it yet, so don't be too anxious to write everything down, because we'll go through it again and label it. And then the loop of Henle is going to turn into another round of tubes called the distal tubule. And then the distal tubule is going to turn into a long tube called the collecting duct. And the collecting duct is going to go all the way down the renal pyramid. And it's actually going to it's going to end at the renal papilla. So this is the collecting duct. See, I feel like so it's kind of like a maze. And you're probably saying, well, why is it so twisted like this? And the answer is surface area. Because as you know, the greater the surface area, the more room there is for things to be absorbed. Since the body is very compact and must stay compact, we rely on highly folded structures to make sure there's enough space for everything to be absorbed. Now we have a couple terms that we need to talk about. Now, excretion is what happens here when anything goes down the collecting duct. But excretion is when substance is removed from body. So that's excretion. Now, using the nephron as an example, there's also something called secretion, which is where something is taken from the nephron and it goes back into the blood. So we call that. Oh wait, no, I'm sorry. I messed that one up. Sometimes things can go from the blood into the nephron. I know this is complicated. But if anything goes from the blood into the nephron, we call that secretion. And if anything goes from the nephron back to the blood, we call that reabsorption. And the reason why it's called reabsorption is because it was already absorbed once in the gut, because everything you eat goes into your blood. So when something is absorbed from your digestive system into the nephron, the digestive system into the blood, we call that absorption. Now, when it goes into the nephron and then back into the blood, we call that reabsorption. All right, so let's talk about some nephron anatomy. And so what I'm going to do here is I'm going to take this nephron and I'm going to draw it very long ways to put it nicely. So this is going to be like a uncoiled nephron, so to speak. So the Bowman's capsule. Now we have the proximal tubule. So notice how highly twisted it is. Then we're going to go to the loop of Henle. Now, if you look here at the loop of Henle, it actually gets narrower as we get to the bottom part of the loop. It's going to get thicker again as we come back up. Then we have the distal tubule. And then we have the collecting duct. Now, first, let's talk about the proximal tubule, which I'm going to shade here in, let's just go with a nice blue. So the proximal tubule is actually where most of the stuff is going to be reabsorbed. So in the proximal tubule, out of all the filtrate that goes into the nephron, well, actually, let me draw the blood first. And these blood vessels also kind of follow around the nephron. Now, the proximal tubule, actually, we are going to have, out of all the stuff that enters the nephron, 70% of H2O is reabsorbed. Now, actually, I'm just going to say if it's reabsorbed. So this is what's going to be reabsorbed. So about 70% of water, but also 70% of ions such as potassium and sodium. Now, the reason why the ions matches the amount of water is because the only way to move water back into the blood is to drag it along with sodium. Because in the human body, I don't believe there's a way to actively pump water. Instead, you need to establish an osmotic gradient using sodium to drive water back into the blood, which is why there's about an equal amount of water and ions reabsorbed. And water really likes to follow sodium for that reason. Now, under ideal circumstances, you should have 100% of glucose, which is when your carbohydrates are completely broken down into your simplest parts. They go in as mainly glucose and also amino acids. Some of you may know that diabetics, one way that diabetes is diagnosed is if somebody has sugar in their blood, if they have glucose in their blood. And that's because there's only so much surface area in the proximal tubule. And remember that the filtrate is going to move through the nephrons at a certain speed. So there is too much glucose dumped into the nephron, then there's just not enough time for it to be reabsorbed, because the proximal tubule is the only place where glucose can be reabsorbed. So the more glucose there is in the blood, the more glucose there is in the nephron. The more glucose there is in the nephron, the less time there is for it to be completely reabsorbed. And also 100% of amino acids are reabsorbed. The body's worked very hard in order to ensure that these are reabsorbed. So these are the main things that are going to be reabsorbed in the part of the proximal tubule. There's more, of course, but I don't really want to overload you guys on information. And the proximal tubule is this part here that I'm kind of shading in. Now, the loop of Henle is very interesting. So we'll go ahead and shade that in this bright green color. The loop of Henle is interesting because each of these sides here, this side here is called the ascending loop. Apologies, descending loop. And this one here is called the ascending loop because that is the direction that water is going. And what's interesting about the descending loop is it only has the ability to reabsorb water. So it reabsorbs water only. Now, the ascending loop is interesting because it only reabsorbs ions and urea. Even though urea is a byproduct of protein metabolism, it's a rather big molecule, and the kidneys use this to its advantage to make sure that the renal medulla, the middle part, is extremely salty, very hypertonic, and that helps with water reabsorption. But it's interesting that the ascending loop takes care of the ions and urea, and the descending loop takes care of the water. So the descending loop cannot reabsorb ions or urea. The ascending loop cannot reabsorb water. So it's kind of like it's allocated to each side of the loop. Now this part up here is called the descending loop. And here, I'll just write the descending loop here. And the descending loop what this does is it is the part that is under hormonal control. Oh, I would be remiss if I did not add that in the loop of Henle, approximately, I would say maybe 22% of H2O and ions is reabsorbed. The descending loop is under hormonal control. And what that means is that the amount of water reabsorption is variable. So H2O ion reabsorption variable. So if somebody has had too much water, as in the individual has too much water in their blood, then what's going to happen is that certain hormones are going to be secreted in smaller quantities, which will encourage the nephron to excrete more water as urine. But if the individual does not have enough water and the body wants to conserve water, then it can release more of certain hormones and cause blood to be, or cause water to be put back into the blood. And that is called, those two hormones are aldosterone and vasopressin. What they do is that they act on the descending loop, and they encourage it either to reabsorb more water back into the blood or to leave the filtrate in the nephron tubules and excrete it through the collecting duct. So it's variable because anywhere from, I don't know, around 1 to 7% H2O is going to be reabsorbed. I should say H2O and ions. Okay, and lastly is the collecting duct, also known as the CD, if you want to abbreviate it. And the collecting duct is basically anything that stays in the collecting duct is going to become urine. Actually, it is, there's still a chance for some things to be reabsorbed in the collecting duct. But generally, I teach even my physio students that just to keep things simple, just go ahead and assume that it doesn't, that everything that's in the collecting duct just becomes urine. And as I was saying, is that this is only one nephron. In the renal system, there's actually hundreds of thousands of nephrons, and they're contained once again in the renal pyramid. Their job is to filter out your blood and then return what is necessary. So, if you want a summary or an analogy of how the nephrons work, think of your blood as a garage, and let's say that if it is a garage packed with boxes. Now, let's say it's time to clean that garage. Well, it's probably easiest to take everything out of the garage and only put back in what you want to keep. And that's basically how the nephron works, is the filtrate, a large amount of the filtrate is dumped into the nephron, and then the body takes back what it wants. And what it doesn't want stays into the nephron and is excreted as urine. What that also means is that for those of you that take those fancy vitamins, if you find that your urine is actually a very dark yellow color, it's because the excess vitamins have been put into the nephron and not reabsorbed. Because water-soluble vitamins, if your body has enough of the vitamin, what's left is just going to go into the nephron and not get brought back out. So what you have then is you have urine that's slightly more expensive. All right, well, I hope you guys enjoyed this lecture. Next up is nervous system, and we'll see you again soon.